Hello everyone, Jim Malis again. We are going to talk about, try to summarize from the Katz book, first edition of the Katz book for calculus-based physics, mechanics, chapters 12 and 13 pertaining to rotation, kinematics, dynamics, how energy considerations get taken into account. Basically, I summarized chapters 12 and 13 from the Katz book for Physics 209, chapters 12 and 13, rotation, and rotational dynamics. So let's just try to get a gut feeling for what's going on here. You guys already know I'm a big fan of the problems are kind of first and foremost. You've got to know how to do the problems. Well, let's know the theory at least some level, at least a decent level, and then when we jump into the problems, the theory comes out. The theory comes out in the actual problems when we're discussing it. So that's a lot of what we're planning to do vis-a-vis a lot of this stuff. So looking at chapters 12 and 13, and like I said, I summarized it by the title of Rotation and Rotational Dynamics. What can we say? You know, what's some pretty interesting stuff regarding some of this? We can basically, I mean, there's almost a lot of ways we can go here. Let's kind of hook around. Let's look at some of the stuff from the past, and then keep talking as we do that. So looking at some of this stuff from the past, let's review it a little bit, then build on it a little bit, and we'll see what we can do from there. Again, guys, I mean, we remember some of the basics of what we had said. I mean, some of the basics that we had done. Some of the basics of what we had done, and we had said if, a vector is a sub x I hat, a vector equals a sub x I hat plus a sub y j hat plus a sub z k hat, and b vector equals b sub x I hat plus b sub y j hat plus b sub z k hat. A sub x, a sub y, a sub z, b sub x, b sub y, b sub z are all scalars. They're all scalars. The I hat, j hat, k hat are vectors, and when you multiply a scalar with a vector, you get a vector. You just get a longer vector than the unit vector, or a shorter vector than the unit vector, or maybe the same length vector as the unit vector if you multiply them by 1. That's all it is. So we looked at this, we talked about some stuff. It's debatable how we want to do this, how far I want to go with this when we're talking about it. Let's see how this proceeds, and we'll see what we can do. We're definitely going to get a good feeling for what's happening here. We said that a vector dot b vector, that's not multiplication, it's a dot product. It's a special kind of multiplication. That's magnitude of a times magnitude of b times the cosine of theta. And we said that is ax bx plus ay by. I promised you there's a beautiful derivation of it, but I can't tell you what it is right now, given the time constraints we have. But there is some beautiful mathematics that gives us that derivation. They don't just make it up because it looks convenient, obviously. So we're looking at something like this. And see what else you could say. If you had a vector, and let me just see how I want to do this. A vector cross B vector, and here goes. I mean, there's a number of ways to do it. Again, it's one of those things, guys. How much time do we have? And to show some of it, you could take it And you could say, you know, I got AX I hat plus AY J hat plus AZ K hat. And if I'm crossing it with BX I hat plus BY J hat plus BZ K hat, you can actually you could take the AX I hat and distribute the cross product over here and get an answer, and then do the same thing here with this guy going here and here and here. Just got to determine what the cross products are. And again, I'm going to run out of room, guys. Let me kind of take that guy and go over here. Maybe, sorry for the multicolors, multi-directions here. Basically, you can distribute things across multiple times the way you do normal multiplication, but you got to do a cross product each time. Well, the crazy stuff that happens here, you know, we got to remember in the past, guys, if I was taking I hat dot I hat, I get 1. But I hat dot anybody else that's not in line with it, that's not parallel to it, anybody, you know, I hat and J hat are perpendicular to each other. The dot product of things that are perpendicular to each other, if two things are perpendicular to each other, the angle between them is 90 degrees. What's the cosine of 90 degrees? It's 0. So all these are going to be 0. And I think I've already said this, you know, but I think it just bears mentioning again. So you come over here. I mean, you go J hat dot I hat, get an answer, and it's going to be 0. Only J hat dot J hat is going to give you 1, and J hat dot K hat also going to give you 0. So only this guy is going to give you 1. Only that guy is going to give you 1. If you want to come over here, K hat dot I hat, that's 0. K hat dot J hat, that's 0. And only K hat dot K hat will give you 1. All right. Oh yeah, and this is commutative, guys. It doesn't matter the order. It never matters the order that you do a dot product. A vector dot B vector. A vector dot B vector is the same as B vector dot A vector. The dot product is a commutative phenomenon. It's a scalar. At the end of the day, it will give you a scalar answer. And the order in which you dot two vectors does not matter. Whereas the cross product, so the dot product is commutative, whereas the dot product's commutative, whereas the cross product is not. When you're doing a cross product, like A vector cross B vector, you're going to get the same magnitude, but it's equal to the opposite of B vector cross A vector. So the cross product is not commutative, but the dot product is commutative. Okay. When you're doing some of this stuff. So it's pretty important in that regard. If you were doing, here's another thing with the cross product that's kind of weird. It's kind of just the opposite of the other one. I hat, when two vectors are in line with each other, they go to the 0 vector. When they are perpendicular to one another, so there's always the right-hand rotation going on, guys. And now here's where we got to be extremely careful, I guess you could say. You've got, here's I hat, here's J hat, and this guy comes out this way, here's K hat. And you always go right hand, and as you roll your right hand, your thumb will point to what the result is. So I vector cross J vector is K vector. I vector cross J vector is the magnitude of the two times the sine of the angle between them. Well, the sine of 90 degrees, these are all orthogonal, the sine of 90 degrees is 1. Yeah, and if there's no angle between them, it's 0. The sine of 0 is 0. The sine of 0 is 0, but the cosine of 0 is 1. So when they're right on top of each other, for dot products, when they're right in line with each other, it's a 0 degree angle. The cosine of 0 is 1. So if they're the same, you'll get 1. Here, if they're the same, you get 0, because the angle between them, in both cases, the angle between them is 0. But this is the cosine of 0, which will give you 1. This is the sine of 0, which will give you 0. The only guys that work is when they're orthogonal to each other. So I vector or I hat cross j hat is k hat. Roll your right hand. Bam. Roll your right hand. Your thumb will point in that direction. Then go. I'll tell you what. Let me just do this. Might be a little easier way to do it. I hat j hat. I hat cross j hat. I hat cross j is k hat. So I hat cross j hat is equal to k hat. I hat cross j hat is equal to k hat. J hat cross k hat is I hat. J hat cross k hat is I hat. K hat cross I hat is j hat. Let's just go down, just go around the whole thing. K hat is j hat. Yeah, absolutely true. Absolutely true. What if you go the other way? What if you go j hat cross I hat? J hat cross I. Right hand, guys, roll the right hand and go that way. Oh, those are negative values. J hat cross I hat. That's negative k hat. So it's still in the same line of action. K hat cross j hat. Roll. Oh, it goes that way. That's negative I hat. Let's see here. So we did this. Let's go I hat cross k hat. Goes down. That's going to be j hat, negative j hat. I hat cross k hat. It's going to be negative j hat. They're all the same magnitude. They're all on the same line, but things change. I already kind of told you that. If you reverse them up, they're going to be the opposite. If you ever are talking about I hat cross I hat, or j hat cross j hat, or k hat cross k hat, 0, 0, 0. It's always magnitude times the sine of the angle between them. What's the sine of any angle? What's the sine of the angle between I and I? 0. They're right on top of each other. The sine of the angle between j and j, between k and k. I hat and I hat. J hat and j hat. K hat and j and k hat. Between them, 0. So the cross product when they're the same is 0. The dot product when they're the same is 1, because the cosine of 1 is 1. Whereas here, the sine of 1 is 0. So that's some of the stuff they're talking about there. Well, this is one way to do it. This is kind of, it works. It works. I'm kind of limited on the time to show you. When you do this song and dance right here, it's going to come out pretty good. It's going to come out all right for us. What we can say is, all right, guys. Sometimes the chalk erases well. Sometimes, as you can see, it does not. Let me see what I can do. All right. We'll cross every bridge as we have to, I guess. Let me see what I can do. If you're looking at it like this should be good. This chalk's not bad. It's not ideal as far as contrast, but I don't want to be getting in a situation like this, you guys. So if you were doing A vector cross B vector, you could write it as let me see how I want to write it. All right, let's see what we can do. A vector cross B vector is I hat, J hat, K hat. And what we got here, I hat, J hat, K hat, A sub X, A sub Y, A sub Z, B sub X, B sub Y, B sub Z. And you saw me do this, you've seen me do this before. This thing right here, if you play the cards right, is the same as this. This is just a little memory trick for what's going on right here. They are identical. This just fortuitously, in a sense, this pneumatic device, memory trick of this right here, of this determinant, yields the same thing as here if you take the mathematics as you're supposed to take the mathematics right here. There's a lot of ways to go here, and the proofs are, as I said, rather fascinating. Fascinating, beautiful stuff, takes kind of forever, but not really hard, but they do take forever. Not our business right now. So when we do this, we're getting I hat leading the show, I guess you could say. And we said, you saw me play this game a little bit. Row 1, column 1, 1 and 1 is 2. So it's going to be AYBZ. Then it's going to be minus AZBY. So there's a little pattern once you get the first one. You go here, column 2, row 1. 1 and 2 is 3. That's why I got the negative I hat, negative J hat rather, I'm sorry. AXBZ minus AZBX. Minus AZBX on that. The other one is K hat. Row 1, column 3, 1 and 3 is 4, it's even. It's going to be positive. It's AXBY minus AYBX. I mean, there's kind of a pattern once you write that thing. So AXBY minus AYBX. Sounds good. That's the whole thing. I cannot emphasize how beautiful the theorem is that leads to this, and how this thing right here, if you were to use the Pythagorean theorem and square that scalar right here, ignore the I, that whole thing, this whole mess right here, square it. This whole mess right here, square it. This whole mess right here, square it. Ignore the vectors. Add all the squares together and get the square root. That is equal to the magnitude of the cross product vector. And the magnitude of that cross product vector is AB sine theta. If you were to take A by itself, find out how big it is. Well, how big is A? A is, ignore the I hat, J hat, K hat, and all these. Go AX squared plus AY squared plus AZ squared. Add those together. Take AX squared, AY squared, AZ squared. Add them together, get the square root. That's the magnitude of A. That's the magnitude of A vector. Just call it A. Take BX, square it. Take AY, square it. Take AZ, square it. Ignore the I hat, J hat, K hat. The square of BX, the square of the square of BX, the square of BY, the square of BZ. Add them together, and then square root that sum. Square root the sum of all these squares, the ax squared, ay squared, az squared. The sum of those squares square rooted is the magnitude of A. The sum of bx squared, by squared, bz squared, that sum square rooted is the magnitude of B. Theta is the angle between those two vectors, A and B. Magnitude of A times magnitude of B times the sine of theta will give you this, the size of this vector. What's the size of this vector? Take that mess, square it. Just here, ignore the I hat. Just take all of this, square it. Take all of this, ignore the j hat, square it. Ignore the k hat, take all of this, square it. Add them together, get the square root, it's as big as this. This also tells you the direction in which it goes. So if A vector does this, and let's say B vector did this, and that's theta, A cross B comes right out of the board. A cross B, bam, comes right out of the board. A cross B comes right out of the board. B cross A goes right into the board. It's the same size though. Same exact size vector, just going in an opposite direction. So on and so forth, you guys. Pretty fascinating stuff. Pretty fascinating stuff regarding all that. So this is, where you want to go with this. I mean, there's a lot of places to go, guys. I got to kind of pick the battles on how to do this. I really wish we had a lot more time. Let me at least give you some of the highlights of where this is kind of interesting because, let me make a couple general conclusions here, and maybe that'll explain some stuff that's going on. You guys know, so okay, I said what I said. Keep this here, and that's what this is. You guys, let's say there was two functions. Let's say there was two functions. A function A sub x, A of x, scalar. This is, maybe I should write some other way, maybe. Two functions. F function, that's f of x, and g function. If I were getting the derivative of this function with respect to, that's a good point in its own right. Let's do let's get the derivative with respect to t, I guess you could say. Derivative of that function with respect to t. Let's say it was a function of t. So much in physics is a function of time. So if you're looking at it, you'd actually get, what do we know? Well, we know that in general, the derivative with respect to anything, we'll call that prime, right? FG prime, the derivative is f prime g plus g prime f, or simply just f g prime. Let's just kind of leave them in order. So if I was doing that here, I'd get d dt of f times g plus f d dt of g. And if you want to write it as a shorthand, you're writing something like that. Well, what you can do, there's a lot of arguments here, guys. I'm kind of arguing with myself how much I need to show you. It might be perhaps erring on the side of caution, doing a little bit of overkill is not going to be a bad way to go. But let's see. You saw what I just said right there. This is kind of, there's so much to say, guys. Absolutely so much to say. Let's try to say something about it. This is true. Therefore, let me just say some stuff. That is indeed true. So can we generalize that to the dot product and to the cross product? Can we generalize that? What am I talking about? Well, if I was going d dt of A vector dot B vector, is it possible to draw this conclusion? D dt of A vector as is dot B vector plus A vector dot, so the time derivative of A vector dot B vector, and here it's A vector Can you say that? I'll tell you up front right now, yeah, you sure can say that. How it gets proved, I don't know. I'm still debating this, where you want me to go. I'm going to tell you it's true. I'm certainly going to tell you that it's true. And, so we got this. You're telling me it's going to be that plus that. Yeah, absolutely I'm making that claim. If this right here, A vector dot B vector is given by AX BX plus AY BY plus AZ BZ, then you could individually get derivatives. You could say, okay, watch. This is, again, I'm kind of just debating this with myself, but what the heck? The Greeks have a saying, bikos to horotha horepsis. If you enter the dance, you dance. Let me enter the dance. AX BX. That's a scalar, whatever it may happen to be. AY BY, another scalar. AZ BZ, another scalar. These are scalar functions. If they're functions of t, they don't have to be constants. I've been working with constants all along here in regard to the dot product and the cross product, but I don't have to. I can work with functions, plug in a value of t if it's a function of time, or plug in a value of x or y or whatever it's a function of, usually a function of t. Plug in a function of t, and then I don't have a function anymore. At that particular point, they're constant values. But what happens in terms of a function? Well, you've seen me. If there's functions, treat it like functions. This is a function, that's a function. This is another function, that's another function, different from the other three over here, etc., etc. Isn't the derivative of a sum the sum of the derivatives? The heck does that mean? Well, that means go AX BX and get the derivative of AX BX. Well, I'll tell you what that is. That's dAX dt times BX plus AX dBX dt. Yeah, true. Now, that's what I did right here. That's what I did right here. What about that? And what about the other one? Man, it's the same thing. It's the same thing. AY BY you know where I'm going. Here it's a Z situation. It's the same argument, ladies and gentlemen. The actual specifics are different, but the general format of doing the derivative is unchanged. Okay, great, Melis. How does that have anything to do with this? Well, I can make it look like that, and I can make it look like that added together. I can make those look like that. Really? Sure. I can take this right here, and this right here, and this right here. Notice B vector is BX plus B. B vector is BX I hat plus by j hat plus bz k hat. When you dot product, it's just bx on top of ax, by on top of ay, bz on top of az, and these guys right here, when you do the derivative, are d. You know, let me kind of do the first one to kind of let you see it. It's the same argument. This right here, you guys, is d of axi plus ayj plus azk. Okay, yeah, I guess so. dt. And that's going to be dotted with bx plus by plus bz. Here's k hat. Here's j hat. I ran out of room, guys, so let me write them right. So this is bx I hat, by j hat, bz k hat. When you actually do these, this right here becomes ax dax dt I hat plus day dt j hat plus daz dt k hat dot bxi hat byj hat bzk hat. When you do dot products, guys, don't the x's all come together and you lose the I hats? Don't the y's come together and you lose the j hats? Don't the k's come together and you lose the k hats? And you end up getting dax dt bx, day dt by, so dax dt bx, day dt by, daz dt bz. Yeah, you sure do. Absolutely, and you add them together. Well, we just said that. We just said that. We end up getting let me just kind of look carefully, guys, that we can say here. Right. Yeah, that actually tells us a lot. I mean, if you do this right here, bam, it's the problem solved is what it is. This guy right here, all of it, whatever this thing is, and whatever that thing is, lose the I's, lose the J's, lose the K's. Lose the I hats, the J hats, and the K hats, and you got dax dt bx, day dt by, daz dt bz, and this is what it is. I mean, let's see. Let me just see here, guys. That's okay. Let's be careful. Let's be careful. That tells us this. Forgive me, not quite done. Kind of jumped the gun on that one. dax dt bx, day dt by, daz dt bz. So dax dt bx, day dt by, daz dt bz is this. All right, guys, so it's this, and it's this guy, and it's this guy. Okay, great. That's only half the ball game, Malus. How are you getting this one? How are you going to get that one? And then how are you going to get that one? You got half of them. You got 1, 2, 3. Now, find out the other 1, 2, 3. Find out the other 3. You got the first 3. Well, what I did was I took the derivative with respect to t of a vector. If I take that and leave it alone and now leave a vector, forgive me here, let me see. Forgive this, hold on, let me see what I got. I got this, that's k hat, j hat, All right, guys. I forgot how to write letters. Okay, so we got this. And then you're going to say, okay, let me dot that with dbx dt I hat, dby dt j hat, plus dbz dt k hat. If I'm dotting it, the ax is going to hit bx dt. The ay is going to hit dby dt. The az is going to hit dbz dt. The ax is going to hit dbx dt. The ay is going to hit dby dt. And the az is going to hit dbz dt. We just found the other three, so it works. This is not the best way to say this. I wish we were in person. We could talk more. That we could maybe have a little bit more blackboard space, and we could argue this a little bit. But that's essentially the argument, you guys. It sure is true. Let's get it really clear, guys. This that I said sure winds up like this. Wow, that's analogous to you guys. Okay, guys, I'm trying to, some of this chalk is just not the best. That's analogous to this. You know, as we said, try to write over this, maybe make it look something more manageable. F prime G plus F G prime. Absolutely, it works just like that. It works just like that. Well, yeah, it's true. It is true. You know, you more or less saw it here. Takes a while. You could sit down on your own and confirm that based on the definition of the dot product that I've given you. And then later on, you can confirm that for the cross product based on the definition of the cross product that I've given to you. Well, for the cross product, you know, it's its own dynamic, I guess you could say. What to erase, what not to erase, guys, you know. So well, I just told you what happens with the dot product. We talked about it. Wasn't the prettiest thing in the world, but I think we got it. I think we got a path to actually explore it further if you want to do so independently. At this point, get the problems right, guys. You don't need to know all the proofs. Sometimes you take the proofs on faith. These guys worked on it. They got it right. How can I apply it? The problems are going to be challenging enough as is. So we'll figure that one out. Well, you know, it's the same argument, you guys. Let me try. Say something else. What if you got this? Is it gonna be analogous to this? Remember, this is kind of how I started. This is how I kind of started the whole song and dance. Can you do the product rule? Does the product rule work with the dot product? Yeah, we more or less proved that it does. Does the product rule work with the cross product? Is it going to work like this? Wow, you know, A vector cross dv vector dt. Is it going to work like that? Answer to the question is, just like the product rule with scalars, just like the product rule with scalar functions works in the manner of the derivative of fg is the derivative of fg is the derivative of f The derivative of the product FG is the derivative of F times G plus F times the derivative of G, the product rule. I said it worked up here. We proved it. It works for the dot product. It also works for the cross product, you guys. It also works from the cross product. Yeah, I mean, let me give you, don't know how much I want to argue this point, but let's argue it a little bit. Absolutely guarantee you, if you do it right, you can derive it. Well, that's like anything else, I guess. I mean, if you do it right, you can get it right, right? How the heck is that going to work? Well, the way it's going to work is you're going to say, okay, Malus, how's this thing going to work? I mean, I know that this thing is whatever it is. If you were going to get the derivative, this is A cross B. This is A vector. This is A vector cross B vector, and I got this whole song and dance. If you take the time derivative of this cross product, you will individually take the time derivative of this scalar function composed of the product of two scalar functions. This makes it a vector at the end. You will do the same thing here. You'll do the product rule here, here, there, and also over here and over here. You're going to do the product rule 6 times. You're going to respect each particular location. There's 2 of them in the I-hat realm, 2 more of them in the J-hat realm, and 2 more of them in the K-hat realm. Well, if you do that, if you do this product right here, so on and so on and so on, try to exactly think what you would say. I think I need to erase a few things here. Okay, so let me start erasing and then start making some, and then drawing some conclusions. I'm going to go not quite as rigorously as I want to go, but I think it's rigorous enough that you're seeing this, and then when I draw some conclusions later, this is probably, even for the guys in the calc-based version of this stuff, probably a little bit more than you need, but I mean, you can argue that. I don't know. Myself, I like to see derivations as much as possible for me to actually believe what I'm doing sometimes. It's my thing on that. Each one of these is different. So what the heck is going on? Well, let's think. Let's think. Maybe we can be slick about this thing. If you were to take like that, and we got a whole bunch of stuff here. We've done a whole bunch of stuff. We know all this. It's a fascinating point in its own right, you know, how this would play out. If you're doing the time derivative of it, you'd be doing basically, just let me put the carriage in front of the horse, guys, a little bit. When we do this, you are going to be able, you can, if you wish, draw this conclusion, and we're gonna point to it at least, hopefully relatively strongly. We're looking at this. We're looking at. So let me see here. We're looking at that. Yeah, we already said that's true. We're going to prove it. And that can be as you know, how's that pneumatic device go, guys? How do we actually work this thing? How's that work? Well, that guy right there, you can make it this way. DAX dt, day dt, daz dt. And you got the bx function here, the by function here, the bz function here as is, plus, and let's just get rid of some stuff, guys. We kind of, I mean, this is a great room. Wish I had just a little bit more blackboard space, but man, it's a whole lot better than nothing, man. It's still a great room. You know, so we're saying this is what that was that we had. That eventually might get erased. Okay, we talked about this. And that would be the same as I hat, j hat, k hat. I do not want to erase this stuff, guys. I'm going to have to make it a little bit smaller. This is just ax, ay, az, and this is going to be dbx dt. I absolutely do not want to erase this, but I am going to have to. Put that elsewhere, I guess. Dby dt, bbz dt. Let me just give a little bit. There's no. I'm just trying to make the aesthetics a little bit better. Here we are. Here we are. And there it is. That's the claim. This is the pneumatic device. All this is that. All of that is this. All of that is this. And that's just a little memory trick on it. That's great. Do you even believe it? I mean, that's the thing. Can we say it's even true? Well, it is. It's going to come down to that. Because if you were doing something like that, guys, again, there's I guess a great number of ways to go here. Let me try to think. I mean, how I'm going to say this. A hat cross B hat, A vector cross B vector, and we said the whole song and dance, guys, how that's going to play out, right? That one right there is going to be, as we do the cross product, AYBZ, AZBY. AYBZ minus AZBY. Sorry, I'm writing it again, guys, but I kind of got a little pressed for time there. Pressed for area where I want to write some of the stuff. So it's going to be AYBZ minus AZBY plus a negative J hat, plus a negative J hat, rather, right? Plus a negative J hat, AXBZ, AXBZ, AZBX. AZ, let's see what I just said here. I hope I said something right. AXBZ, rather. AX BZ, AZBX, plus K and that's going to be AXBY, AYBX. All right, it's a mess. Is it true? Does it work? If you find, I think if you can do it for one of these, you just by extension do it to the other 5 to get all of these. How would this thing play out on each one of these when you do it? You end up finding that in regard to all this, you guys, let me just kind of okay, so we got it looking like that. If it's doing this, what is going on here? Well, we're making the claim that this is going to happen with that, and that's going to answer, or at least point to a lot of the answers to a lot of questions. Because later on, now, you wonder, why is this so, why is the cross product and dot product so elaborate, especially the cross product? Because this stuff arises in physics. They found it in a natural phenomenon, like I've told everyone. I'm saying it again. I mean, they found it in a natural phenomenon, so they figured at that point, they figured that, we got to get some math to describe some of the physical phenomenon that we're encountering. And this is some of the math that's going on there, you guys. I tell you what, man, let me just, it's the sum of 2 vectors. Sum of 2 vectors, so I'm sorry, it's the sum of 2 functions, also the sum of 2 functions, et cetera, et cetera. Let me go AYBZ. Let me just individually, the derivative of a sum is the sum of the individual derivatives. The individual derivatives have to be attained in these circumstances by using the product rule individually. Product rule here, 2 things will happen. Product rule here, another 2 things will happen. Product rule here, another 2 things, et cetera, et cetera. You're going to do that 6 times, and each one of those 6 times has 2 things happening. Whoa, okay. Well, AYBZ with the product rule is going to give you, let me just see how I want to do this. AYBZ is DAY, let me see, forgive me here. Yeah, AYBZ. Yeah, you can tell this is going to be fun. I wrote the wrong letter to begin with. All right, here we go. DAYBZ. That's true. Plus AY DBZ. True. Plus, I say minus, plus a negative on this one, or, I just say plus a negative I, because this guy had a minus. There's a minus, and I'm going to take them out, and I got AZBY. And I got AZBY. Okay, that's all together. you're going to do, and that's all of it. That's all that's plus. That's these guys added. Wow. You're going to do that 2 more times. I'm going to cross over into here, guys. I'm going to run out of room again. It's going to be J. Well, here you got to be real careful. There's a negative J right here, so I don't. We can play a whole bunch of things on this one, guys. We can maybe, if we got this going on, let's put the I right here. Let's take the I on the outside. Let's take the I on the outside, and it's on the outside. It's going to come into everybody. Yeah, it is, but that's got to be a minus because it was a negative I right there. And that's how we're going to play this. Tell you what I'm going to do. I'm going to take the J, put it out here, and put a negative on it. I'm still going to honor that that's right there, and then play the game. And then play the game. AX, BZ, right off the bat. AX, BZ, and you know the song and dance here. AX, right? That's a minus right here, don't forget. Plus, let's see what we got here. We got, yeah, that was that one. Minus, plus a negative or minus or whatever you want. Let's say minus. They're using minus. Minus the AZ business, AZBX. AZBX. Yeah, there's a minus on that one. So you got this, you got that, you got this. You know, guys, I don't know, it's not pretty, but you see what I'm doing. I think you see what I'm doing. Let's go. Let's get this guy under control. AXBY. You know the deal. Minus AYBX. You're taking the derivative there. It's a sum of all those. If I'm taking the derivative of a sum, any derivative of a sum is the sum of the individual derivatives. So I'm taking the sum of all those individual derivatives. The derivative of an entire sum, no matter how complex it is, the derivative of an entire sum is the sum of individual derivatives. Well, the individual derivatives are themselves asking us or telling us, or the derivatives we're finding, the individual derivatives that we're finding, we're doing the product rule 6 different times. 1, 2, 3, 4, 5, 6. But the sum of all the derivative of all the sums is the sum of all the derivatives, and the derivatives that we're getting derivatives of products, which themselves, the product rule is what it is. You've seen it. I've talked about it. So if this is the case, AXBY, AYBX, AXBY, AXBY, AYBX. So this stuff is, well, I mean, I'm not going to be as cavalier to call it easy, because it's not. AYBX plus AY DBX. Okay. Well, okay, I just wrote brackets. I got brackets and well, whatever. It looks like a foreign language, but I did it. You see it. I think we can see around what I'm trying. What am I saying at the end of that entire song and dance, you guys? This is a big thing. This is a big thing, but it's very doable. At the same time, it's very doable. Saying that's the memory trick. That'll get this right here that's the memory trick. Is it true? Let's do it. Let's do it very carefully. Very, very carefully. I-hat associated with the top guy is that. J-hat associated with the top guy is that. K-hat associated with the top guy is that. Do you see a DAYT? Do you see a DAYDT, a DAXDT, and another? Well, let's put it this way. Do you see, if you cross that out, do you see DAYDT BZ? Sure do. Do you see a minus DAZ? Let's see. Right. Okay, let me try that one more time. It should be right. I don't know why I'm having an issue here, but I am. Okay, let's try it one more time. Let's go here with this guy here. Okay, we're going to do all the A derivatives. All the derivatives starting with these guys. And, see how we want to do this. Let me see if I can, let's see if I can account for everybody carefully here. Let's try. Here we are again. Here's I-hat. Cross it over, cross it over. Cross them over, cross them over. DAYDT BZ. Got it. Minus DAZDT BY. That's this guy. I'm sorry. That's that guy. So, here, let's go this way. Forgive me all these geometric figures I've drawn here. DAYDT BZ and DAY, right, this is very interesting. DAYDT BZ and let me just see here. Yeah, absolutely correct. So let's do it one more time. Forgive me, guys. I think it's important enough just to get a really good look at this thing. Here's I-hat. Cross it here, cross out here, cross out there. Here's I-hat. Cross it out, positive answer. DAYDT BZ. DAYDT BZ. Minus DAZDT BY. DAZDT BY. Bam. That's accounted for. That's accounted for right here. Running out of, I don't want to draw too many circles here. These guys are accounted for. Just trying to debate with myself what to put on there. Okay. We've already accounted for these guys. These guys happened right here. Okay, good enough for me. Cross it out here. Cross out here, cross out here. It's going to be a negative. Okay. It's going to be a negative J times DAXDT BZ. DA, cross it out. Let's just go. Let's just do it. Cross out here, cross out there, minus J. DAXDT BZ and DAZDT minus DAZDT BX. DAXDT BZ, DAXDT BZ minus DAZDT BX. DAZDT BX and DAXDT BZ. Hey guys, man, it ain't in the best order in the world, but it's there too. Okay, let's keep going. Let's go over to K. Here, go across. Cross here, it's going to be positive. DAX dt, by. DAX dt by. DAX dt by, there it is. Okay. Minus day dt bx. Minus day dt bx. Hey. Wait a minute. 1, 2, 3. There's a subtraction going on that I, of course, managed to erase. All right, but there it is. Okay. And it was a negative j, all that stuff. So I tried to, it's a little convoluted, but it's there. This guy, this pneumatic device gave me these 3 large blocks. Now this pneumatic device is going to give me the rest. Cross out here, cross out there, it's going to be I hat. AY dBx, AY dBz dt. AY dBz dt minus, let's see here. Yeah, AY dBz dt, AY dBz dt, AY dBz dt, there it is, minus AZ dBy dt. Oh yeah, here's the minus. Here's the minus, guys. Yeah, so it'll catch them. And that, my friends, is this one. I'm not sure what kind. I want to be able to erase this stuff eventually. Don't know how many arguments I want to make here with this stuff, guys. Let me use something here that might work. That's that guy. Let's get it straight, guys. The game we're playing was with the reds. And we're also playing a game with the greens. Okay. Sounds good. Let's keep going with the greens then. Cross out, negative j. AX dBz dt. Let's see. AX. Oh, okay, it's right here. I'm sorry. This is the J. AX dBz dt. Again, let's cross it over. Cross them out. Cross them out. It's going to be a negative J. Cross that out. Cross that out. AX dBz dt. AX dBz dt. Yeah. AX dBz dt is that, and minus AZ dBx dt. Minus AZ dBx dt. Yeah. How's it minus? Because there's a minus sign right here, guys. There's a minus sign right there. And then there's a minus way outside of all of those. Okay. That's okay. That's okay. That minus sign is going to link up with the greens separately, and it's going to link up, and it's going to link up with the reds. So far, so good. Go with the K. 1 plus 3, that's 4. It's going to be even. It's going to be K vector. AX dBy dt. AX dBy dt. It ain't pretty, but you can see it. AX dBy dt, right? AX dBy dt, AX dBy dt minus AY dBx dt. It's all she wrote. It's all there. It's all there. It's all there. All of it's accounted for. The only thing left to show is, yeah, this is a nice pneumatic device. This pneumatic device, if this is AX, AY, AZ, and BX, BY, BZ, and this is AX, AY, AZ, and this is BX, BY, BZ, didn't we say that is the same as the cross product? We'll call this guy another kind of B. Call it B prime. B prime X, BY, B prime X, B prime Y, B prime Z. When you actually do the cross product, this is the cross product you're talking about. The cross product here with this B prime, with this BX prime, BY prime, BZ prime, the memory trick we had, call that A vector, call this A vector, call this B prime vector. B prime vector is dBx dt, dBy dt, dBz dt. All of it works the way I've taught you in the past. Call this A prime vector. A prime vector cross B. A prime X, A prime Y, A prime Z. It works the same way I've taught you. Wow, the stuff works. It is a long story to reach this conclusion, but it does help us out quite a bit when we do stuff like this. You add all this and you're doing pretty good. Are they going to force you to go to that level and make a proof like that? Probably not. It's good to have it in your back pocket, though. It's good to have some of this in your back pocket. So that's where we are. I mean, there's a lot here, and there it is. I mean, here we are again. It's no mystery here, guys. We got it here again. We got it. We played a lot of games to get there. I hope it was worth your while. You're looking at it. That is simply that and that put together. That right there is simply that and that put together. So on and so forth. Okay, good stuff. Really good stuff. You're going to see this later on. It's going to explain a lot of stuff that they do. Because they got various formulas for the torque, for the angular momentum. How do you figure out angular momentum? How do you figure out torque when you're in the rotational realm? It involves cross products. They say, well, I don't know, if I find the torque on something, I don't say, well, I got a lever, I'm torquing on it, therefore the cross product points out that way. It doesn't really point out that way. You're acting in the realm in which you're acting, but they make the vector shoot out in particular directions, so when you add them together, you can actually figure out, if I'm torquing one way and the other force is torquing the other way, we can kind of play some games with that, and the torque is just, the vector analysis is a good bookkeeping method. As far as the direction that other things happen, if I was talking about a magnetic field and a charged particle moving through a magnetic field, in which direction is there a force experienced by this particle because of its motion through the magnetic field? That obeys the cross product. That works vis-a-vis the cross product, as do other things. But even here, it's like a real life move that way. All right, we got this, you guys. Let's say some stuff on this. So when you do encounter this, there's a lot more things I want to talk about that I'm thinking the best way to kind of pace ourselves to do this, there is the book as well, and I'll try to I'm giving as much information as I can and going even a little bit beyond the book in numerous instances. But the book is great, and the book can go in greater detail than I can as well, given the time constraints. But sometimes I'm doing a little more than the book, and other times the book's going to do a little bit more than I do. So you're reading the book. Obviously, you're reading the book, and anything that you do. You pay money for it, you're going to use it, you're going to do great, you guys. Okay, we got all this stuff. Let's keep talking. You can set it up in such a way, guys, that it just makes sense. And that's what we just did. It sure wasn't pretty, but we did it. And I think it's going to help you out. It's going to, for your personal enrichment going through this stuff, it's not just, wow, they just throw this. It looks like it should be fine. It's kind of convenient. Have they made it up? No. It's consistent with the mathematical reality that they've defined. And they can prove it. And they're willing to bet people's lives on it. When an engineer is building a bridge or building an aircraft or a spacecraft or something or anything or a building, this stuff's got to work. It's got to be right. And they test it. And it's as simple as that. It's as simple as that. See what else we can say here, guys. We've talked about, I'll try to make this reasonable for you, I guess. We've said a lot of stuff. We've gone a lot of places, I guess. There is the idea that the average speed times time is going to give you distance. We talked about the average speed being VF plus VI. That's if there's a constant acceleration. We played numerous games, you guys. I don't need to derive that stuff again because you have it elsewhere in my notes, in addition to the book. But we said this. Subtract VI on each side and divide by T. You got acceleration is delta V divided by delta T. Kind of comes out like this. T, delta T. So on and so forth. You also saw me do a bunch of other stuff, guys. We talked about D. D is equal to VF squared minus VI squared over 2A. D equals VIT plus 1/2. Now you saw me, you've seen this practically ad nauseum by this point. You also saw in previous work where I kind of jumped the gun on the whole thing, I derived this in the rotational realm as well. Let me not derive it again. You got it in my notes. I have myself on tape on that. And we see it in the problems that we solve and stuff. So let's just let's mimic. Let's find out what we're saying here. You could say that theta, and man, there's a lot you can say. Let me try to opt for different things we can say here, guys, as we're trying to do this. I'll try to summarize this, because I think the real big, hard thing I wanted to say, I just said, in that derivation that took forever. Let's try to kind of do some of this stuff as is, and we can figure it out. Again, all this stuff gets thrown at us, and we make it make some sense within the context of the problem. So if it's not everything I wanted to say, it's a good portion of what I want to say. And then we clean up, hopefully a decent amount when we're doing some of these problems. In addition to you looking at my notes, both on Canvas and on film, and reading the book, of course. And you're looking at how we do some of the problems. So it's a good way to look at it. I can't wait till I'm in person with people talking about this stuff, whenever that's going to be, So, but as I'm writing this now, as we talk about this now. But anyway, hopefully this stuff is of use for a long time. So if you're already here, I'm just arguing a bit what I want to say here. D looks a lot like theta, and this lowercase omega, the last letter in the Greek alphabet, first letter in the Greek alphabet is alpha, last letter in the Greek alphabet is omega. There's high case, low case. That is a lowercase omega right here, last letter in the Greek alphabet. Theta has a TH sound, sounds like it would have a TH sound. So let's see what we got. Theta equals the average of omega times t. Yeah, we've been there. The average angular velocity, that could be angular velocity could be radians per second, degrees per second, revolutions per second, per minute, per day, per year, whatever. Rate at which an angle is gone through, I guess, for lack of a subtended. The angle that is accomplished in a given period of time. Angle accomplished divided by the time it took for it to happen. That right there, omega sub f omega sub I, and we got this. What does that mean? Well, that means, guys, let me write this down. Maybe this is easier just written down, and then we sort of make it some kind of heads or tails of what the heck's going on here with this stuff. Alpha is angular acceleration. It is the amount of angular speed difference divided by unit time. If you play a mathematical game here and solve for t, you got omega sub f, omega sub I over alpha. So we got what's going on there. What else we got? Well, the D's are a lot like the thetas. Theta is omega sub f squared minus omega sub I squared over 2 alpha. And theta is omega sub I times t plus 1/2 alpha t squared. Sorry guys, chalk's flying everywhere here. So, just forgive me guys, I gotta find out the best chalk to use sometimes. And then chalk that I probably should not be touching. So on and so forth. Guys, these equations, I can set up a one-to-one correspondence between, how many equations up here, guys? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There is a one-to-one correspondence with each of these 7 equations. For each one of these 7 equations, I can find an equation. From each one of these 7 equations, I can find an equation from here, one and only one equation, that looks just like the other one. You know that. D equals V bar T, theta equals omega bar T. Omega bar, V bar is this, omega bar is that. Omega sub F is this, V sub F is that. You get the picture. The way I solved it was I multiplied by R on each side and I found what was going on. Remember, distance was R times theta. Write it as S if you want. D and S are the same thing, D and S. S equals R times theta. ds dt is V. Yeah, and that's this. The R comes out and you got the theta dt. D theta dt is change in theta over change in time. That's called omega. If you multiply omega by R, you get V. If you multiply theta by R, you get S. You get the picture? If you want to go dv dt, first derivative, getting the first derivative of this. The R is a constant, and you got this. Well, change in omega over change in time is the angular acceleration. It becomes R alpha. You could use the product rule if the radius was changing. Radius could be changing. It could be some kind of circular motion, and the radius is getting smaller or bigger. Could be a lot going on. We're not going there, but we could go there. Then we'd have to use the product rule. We've seen the product rule ad nauseum the last 2 hours when I was doing this stuff up here anyway. So you could do that. They called you on it. So on and so forth. It's a lot here. They got this thing called torque. It's a vector, and they call it R vector cross F vector. Wow, I'd never really seen it expressed like that. I just had people say, there's a moment arm of length d. You multiply it by F, and you'll get a torque, F times d. This R cross F means, well, what did we say about the cross product? If the R vector was doing this, and you had a force going straight down F right here, and we can get a little messy. They want them, this is really what's going on, and there's an angle here. Now here it can get a little, things can get a little touchy. We gotta be a little careful here. If you extended this guy like this, R, and this is theta, this right here would be 180 minus theta. One's theta, the other one's 180 minus theta. R vector cross F vector, R vector cross F vector, the magnitude of it is how big R is, how big F is, times the sine of the angle between them, the sine of theta. Ladies and gentlemen, do you guys remember? Here's the sine function. Here's 90 degrees. Here's 180 right here. If this is theta, go theta over here, and if you take away theta, go over here, you're at 180 minus theta. The height is the same. So the sine of theta is the same as the sine of 180 minus theta. So basically, what are they trying to say here? The best way to use a lever is to hit the lever perpendicular. Hit the lever perpendicular and you get the most torque, the most tendency to rotate. Torque is a measure of the tendency to rotate. It's analogous to this thing called force, which is a measure of the ability to move something in the linear direction. It's not really the right way to do it. Force, amount of force is indicative of a tendency to change the state of motion of something in some linear sense. Torque is a measure of the tendency to change the rotational state of something. Torque and force are really similar. Force pertains to the linear realm, tendency to change the state of motion in the linear realm. Force tells you that tendency. Torque tells you the tendency to want to rotate something. So they're analogous to each other. Kind of like alpha and A are analogous. Kind of like alpha and A are analogous to each other. Kind of like VF and omega F and VI and omega I and D and omega, or D and theta, they're all analogous to each other. If you were to take this, if you were to get the sine of this angle, this F, there's a number of ways to do this, but let me show you. If you take this F right here, and go F times the sine of 180 minus theta, I already just said that the sine, that's the same as RF sine 180 minus theta, you know. Okay. Sine 180 minus theta and sine of theta are the same thing. Here we go. Sine function right here. Look where they go. They go right here. Sine 180 minus theta, F times the sine of 180 is this. If you took this and put it right here, yeah, you're hitting it this way. I'm pulling this way. I'd put a lot of torque on it. Yeah, I can't use all the force. Some of the force gets wasted, I guess. You got to go here. You got to go here. You got to go this way and that way. Or you could take this guy and shorten the lever arm and then go straight down. But even here, alternate interior angles are congruent. That's 180 minus theta. So that's where this is coming from. And if you want to find the magnitude of it is this. They like to usually write these things, though it's not convenient. They like to write F vector like that, and they like to write, let's say, R vector like that, and F vector, they like to write, you know, it's a great question. I mean, and then F vector, they like to write like that. And that's the one. That's really the theta they're talking about. That's really the theta. But still, I can kind of bring this. I can pick up that vector and put it right here. And then the 180 minus theta. This thing right here would be theta, and this guy right here is 180 minus theta. A lot of ways to go, guys. That's the torque. There's a lot happening there. Let me try to kind of summarize this somewhat quickly so we can kind of get you guys out of the woods on this. I don't want to be, I don't want to talk for 9 hours straight here, you guys, but I can talk a little bit more, of course, certainly. This is some of what's going on. So when you see this stuff in your reading and in your work, it's not going to be quite as shocking. Okay. We've said something. We talked about torque. Let's try to put some of this stuff together. At some level, let's try to put some of this stuff together and hopefully make it pretty believable for us. All right. Try to see here, guys. Now we've said some stuff. I'm sort of gonna put the carriage in front of the horse on this thing and just kind of put some things together, throw them at you, at least as far as to a large degree what formulas look like. You're going to remember some of the stuff I said. It's a lot to say. I mean, there's an analogy here. I'll say some of the analogies, I guess you could say. In the linear realm, we talk about D. In the linear realm, we talk about D. In the rotational realm, we talk about theta. So there's a connection there. We talk about V. We talk about omega. We talk about A. We talk about alpha. So on and so forth on that. We talk about force. They talk about torque. Everybody across from one another is everybody across from everybody else is analogous to the other one. Here's the linear realm, here's rotational realm. In some places, we got to agree completely. Like when? Well, in more places than you think, and probably more places than I'm going to say. I'll say this much. If work is being done, I don't care if rotation was being done or something else was being done. Work is work, and we got to figure out a way to figure that one out too. Okay. That's a tau, the Greek letter for T. Here's that. Momentum vector, and linear momentum vector, and angular momentum vector. So on and so forth. Crazy stuff. What is it? How does it work? In a lot of instances, here if you multiply by R, you get tau. For these other ones, if you multiply by R, you get over there. So you got to kind of watch it a little bit. They got this thing called mass that we're familiar with. We've been working with it. And they got this other thing called moment of inertia. It is the rotational analogy to mass. Well, it's a rough one to go with. In the notes that I have on Canvas, I actually derive for various geometric figures, I give you a derivation as to what the moments of inertia are. There may be two masses that are exactly identical in terms of their mass, but one of them is, and they're set up on a particular axle, and you can rotate them. Even if the axle is frictionless and you can easily rotate either one of them you can accelerate faster, sooner than the other. You can get a particular omega from rest, a particular angular velocity. You can get it much faster for one of them than the other. How's that? Well, one of them might be really compact, very dense, very compact, and it's not spread out. You could probably, if you have the right grip on it and stuff, you can get that to rotate really fast. Whereas another one, if it was the exact same mass, if it's spread out very much, it's harder for you to get that thing to accelerate, even though the total mass of each one is the same. That's where moment of inertia comes in. I have that derived, and I talk about moments of inertia. You don't have to, I don't think you even need to be able to do the derivations I've shown you. You can do them. How much time do you have? That's one thing. But I mean, as long as you know I'll give you the information as to what the moment of inertia is for something. But if you want to look at it, I do have a discussion about it in my notes, and I do actually prove a number of things regarding moment of inertia. This thing called the parallel axis theorem and some other stuff regarding it. Well, let's talk about this moment of inertia. There's a lot to say. And like I said, I do have the derivations, so I will tell you, go to my derivations if you want to see for different geometric figures how it works. One way to look at it, if you went to the beach and there's one of those things that you can, kind of a merry-go-round thing or something like that, and you put your nephews on it or something like that, family, friends, whatever, they get on it. If everybody goes to the center of the apparatus and you try to swing them around, you can do it with a torque of force times the distance. You can do it with a torque that ain't that big, and you can get it to go pretty fast. But if everybody, and let's say it's a frictionless axle, if everybody's kind of close by, bunched up in the middle, it's easy for you to spin them around. You have them come out. However, to the edges. The same exact mass of the apparatus and people is present, but you're going to have a harder time accelerating them with a particular torque because the moment of inertia has gotten bigger. You can kind of do an infinite sum of, let's say there's an infinitely a very, very strong pole that has no mass to it. There's a mass m at the end of it. Let's just call it small m. And let's say this thing is of distance r. They define the moment of inertia of this point mass to be mr squared. If there's many of these point masses, the moment of inertia is a sum, in fact, an infinite sum, of this nature. In fact, if you want to go to the realm of calculus, it'll be r squared dm. The masses get smaller and smaller, and you can do it. But it all originates right here, ladies and gentlemen. You do an infinite sum with this. And I have this proof. Let's say you anchor this r length pole to something in the universe that won't move. Let's say it's so massive as the Earth. And that ain't going to move. The Earth's not going to, relative to me and the Earth, we're going to say it's not going to move. We'll just say that for the argument. This is anchored really strongly, guys, and this guy's here. How is that going to move? How's it going to move? It's a hard thing to move. It's a lot easier to move this guy if you slide him down here. If I'm pushing from up here, this guy's harder to move than if I bring the thing down there. Yeah, it may be harder to move, but if you succeed in moving him, you're moving him a greater distance than him being down there. You don't get something for nothing, but you also don't lose something for nothing. It's harder to move it, but you will move a bigger distance. It will rotate further. Move it down here, it won't rotate as far, but it'll be easier to get it there. So the work's a little bit different story for the same force that you're using. All right, there's a lot there. I'm going to kind of make a long story short. Do you guys remember that force equals mass times acceleration? I mean, force, I can write force a lot of ways. You know that. That's kind of the challenge here, I guess you could say. Force equals mass times acceleration. Okay. Just trying to make a couple arguments here as to what we could do. Force definitely equals mass times acceleration. I'm not going to get into great detail on that. There's a lot of what ifs, a lot of, hey, wait a minute, let's say this, that, especially with the torque. The angle it's at. If I'm talking about work later on, hey, at what angle are you pushing and through what distance are you pushing? You got to do a dot product. You sure do. Let's get away from that now. We already know we got to do a dot product if we're trying to find the work done. We already know you got to find the sine of an angle. You got to do the cross product if you're finding the torque. I get all that. Let's just say everybody behaves pretty well and I'm not having to find angles here. It's a 90-degree push if I'm finding torque, and it's a 0-degree push if I'm finding work. May I ask you a question? Is torque equal to force times R? The rate, yeah, and it's sine theta. I said theta is going to be 90 degrees. It's F times R. Is F equal to M times A times R? Yeah, I agree with that. Is A equal, in the work we've done in the past, when I talked about this stuff, in an earlier video, is A alpha times R? Remember, guys, we've kind of been playing games. I mean, we've done this in the past. D is R times theta, or theta times R, whatever, whatever aesthetics you want on this. Theta times R. V is omega times R. And A is alpha times R. Is alpha times R. So on and so forth. Well, that's A. Yeah, good enough for me. Times R to get the torque. Wait a minute here. Take a good look here now. R times R is R squared. M is M. And alpha is right here. Let's take the alpha. Take the alpha out of there and go R times M. It's MR squared. Wait a minute, what the heck's that? What is MR squared? Didn't I say that was I? And what's this? That's alpha. And that's torque. Hold on now. I'm seeing something here. We said force equals, let's have a look, guys. Okay. Force equals mass times acceleration. Torque equals moment of inertia times angular acceleration. Wait a minute. Didn't I say that force and torque are analogous to each other? Mass and moment of inertia are analogous to each other. And linear acceleration and angular acceleration are analogous to each other, are similar to each other. Yeah, yes. Look at it. Torque kind of sort of looks like force. Moment of inertia kind of sort of behaves like mass. And alpha kind of sort of behaves like A. Angular acceleration kind of sort of behaves like A. Wow, there's analogies everywhere. Yeah, there's a reason why I wrote it down that way. Now I just showed you why. There's a lot going on. They've got, I'm just trying to argue here. Trying to argue with this a little bit, you guys. There's a lot going on here. I'll tell you what, there's another thing going on here. There is, just trying to figure out a good way to kind of talk to you about this. Let's forget vector notation for a second, and let's just kind of get to the guts of the matter a little bit sometimes. Again, the vectors do matter. I never said they don't matter. Nobody's going to turn around and tell me I said that, right? Right now, let's just kind of visualize something in terms of quote-unquote well-behaved mathematics or well-behaved scenarios occurring here. We did say that F is equal to dp dt, and you saw me do that. This thing called angular acceleration is r vector cross p vector. What the heck does that mean? Be patient with me, guys. Did we say momentum? Momentum is, in terms of vectors, mv vector. In terms of just like a gut feeling, it's mv, right? If something is occurring, remember, in the rotational realm, isn't it essential, ladies and gentlemen, to know what distance you are away from the circle, for lack of a better word, around which you are moving? The further away you are, the more torque you can build. The further away you are, there's probably more of an indication of angular momentum. I'm going to make, that's where this is coming from. In terms of magnitude, the magnitude of this guy, L, is P times R times the sine of theta. All right, PR. Do you understand that if I'm going to write this guy, if I'm going to write this, and I already said this, do you understand you could call L P times R, which is MVR, MVR, that's P times R. And that's where they're getting this. There's something really crazy that goes on here, guys. The rate of change of angular momentum will give you the torque. You know, here we go. I told you it's going to be well behaved. Now I'm not making it well behaved. dl vector, the rate of change of angular momentum. Well, let's just get down to business. The torque vector, just like the force vector, is directly dependent upon the rate of change of momentum. If the rate of change of momentum is great, there had to be a great force. If the rate of change of momentum is not great, there can't be a great force. If the rate of change of momentum is great, a great force created the great rate of change of momentum. If the rate of change of angular momentum is great, there had to be a great torque to make it happen. That's kind of interesting. You don't need to lose an incredible amount of sleep about what I'm about to show you, but it is true. And this is why I was doing that whole big song and dance earlier. Didn't we say R vector cross P vector R vector, the time derivative of R vector cross P vector. Wait a minute, we already did that. What is the time derivative of A vector cross B vector? Remember? dr vector dt cross P vector plus R hat cross dP vector dt. Give myself a little bit more room, guys. dl vector dt, we said that's going to be d dt, r vector cross p vector. dr vector dt cross p vector plus r vector cross, and I don't know how I did it. I wrote right smaller than I wanted to again, but you know where I'm coming from. We already proved that. That was the point of all that work earlier. If you really wanted to go there, we can go there. And we did go there. There's got to be maybe an easier look, at least a gut feeling easier look as to what's going on, you guys. Maybe there's something easier to look at. Yeah, I think there is. I think there is. You know, we've said stuff. I mean, we made some statements. We said what that is, what the torque is, how the torque relates. Okay, yeah, we saw that analogy there. I got to talk to you. Is work? Now we're not going to worry too much, guys. We're just going to say force times distance times the cosine of theta. The cosine of theta is the cosine of 0 degrees. It's pushing in such a manner. Let me see if this is pretty legible. It's a little different chalk. All right, it's good enough. Work is force times distance. I agree. Okay, are you willing to believe something? If I say to you that work is force times distance, force times distance, huh? Tell you what I'm going to do. Is distance r times theta or theta times r? Yeah, we've already talked that. We've delivered that speech in various places. We delivered it though. Distance is theta times r. Why don't you put the r next to the f and go here? What's F times R? F times R is torque. Theta's theta. Okay, hold on. Yeah, there's something here. Definitely something here. In fact, let's write it down. Let me try to conveniently write them close to each other. Here's torque, here's theta. Didn't we say that force and torque are analogous to each other? Didn't we say that distance and theta are analogous to each other? If you want to find work, you go torque times theta if there's a rotation. It looks like force times distance. Force times distance is analogous to torque times theta, and it works. If you wanted to find power, it'd be work divided by time. That would be FD divided by time. Guys, how quick are we with this stuff? D divided by T, yeah, I can link it up like that. F times D is work, and then T's on the bottom. Power is the rate at which work is being done. W divided by T. D divided by T is V. Force times the magnitude of velocity. Great. You telling me I can do that here? Yeah. Work over T. I already talked about torque, I already talked about theta, I already talked about T. Here we go. What is the rate of change of angular displacement? What is the angular displacement over time? The rate of change, the time rate of change of angular displacement is omega. Theta divided by T is omega. Power equals torque times omega. Man, you got to be kidding me. It's happening again. You telling me F looks a lot like torque and V looks a lot like omega? Yeah, we already talked about that. There's analogies all over the place. There's analogies all over the place. So on and so forth. Got a question for you. Okay, you've seen this speech, and we've played a few games here. We played a few games here based on the very rigorous conclusions that we drew earlier. L equals MVR. Yeah, good enough for me. I mean, okay, I don't want to talk about what ifs. Right now, let's get a big picture. Let's get a big picture. You know the rigorous way to look at it. Yeah, we've delivered this speech in different ways already today, extensively. We got this. So we're okay. Can I ask you a question? Is V omega times R? Yeah. V is omega times R. M omega R squared. Well, let's do some MR squared is I. All right, hold on now. Didn't we say that momentum was mass times velocity? Are you telling me, and I'm ignoring vectors right now. Let's look at this. Let's look at the analogy. That's the big thing right now. Did we say that momentum, linear momentum is mass times velocity? Angular momentum is MVR. Yes. And then we played some games with this thing moving around. Well, again, you just saw the song and dance I just did. Linear momentum, magnitude in this case, magnitude of linear momentum, magnitude of linear momentum, magnitude of angular momentum. Mass, moment of inertia. Linear momentum, angular momentum. Mass, moment of inertia. Linear velocity, angular velocity. Interesting. And this happens with that small piece. That small piece, here's the R, here's the M, here's MR squared equals I. Yeah, but when you sum them all together, I can extend this to the sum. I can extend this to a steel sphere, to a lead sphere, to whatever kind of great metal there might be, a golden sphere. I could still get individual pieces. I could find out what the moment of inertia is, and all of this works. All of this works. Okay, I mean, there's a lot being said. Is kinetic energy 1/2 mv squared? Yeah, let's get the kinetic energy of one small piece of mass that is associated with a rotating object. And then I'll sum all of those pieces of matter, the mass of each one of those, infinitesimally. That's an integral waiting to happen, right? But I can sum all of those pieces of matter. I can take it to the limit, and then I can add all those kinetic energies and find out what the kinetic energy of a rotating object is. In the rotational sense, R for rotation. Let's say there is one small piece of matter, M, and V, ladies and gentlemen, is omega R. Square that product. Half is a half. Mr squared, I'm going to put next to each other, and I think you can see what I'm doing. Omega squared right here. I'm not done, but I'd like to stop for a second. There's a lot going on. Definitely a lot going on. Can I ask you a question? That's just one of the pieces. Guys, listen, guys. If something is rotating about this axis, and it's solid, it is solid, everybody stays together, the omega is the same for the mass. The omega is the same for the mass right here at a distance r1, and it's same here for the distance r2, and it's same here for the distance r3, etc. The omega is the same. If I sum all of those r's, if I sum all of those r squareds for a given infinitesimal mass m or dm, that's an integral. If I sum r squared dm everywhere, I'm summing all the mr squareds. If I do that, I'll get the moment of inertia. So if you wanted to make that a summation, the summation of all these guys is going to be a moment of inertia. That's I. That's omega squared. And ladies and gentlemen, let's keep talking. The kinetic energy is 1/2 mv squared. Here we go again. Is a half equal to a half? Does I look like m? Does omega squared look like v squared? Yeah, because omega looks like v. There's analogies everywhere. There's analogies everywhere. And they're there. They're there to be seen. Writing some of them, I'm probably missing some other ones, but this is pretty big. So when you say that for those two chapters, a lot here. But we see that there's an analogy, and we said it. Mass and moment of inertia. Linear momentum and angular momentum. Force and torque. Acceleration and angular acceleration. Linear velocity and angular velocity. Linear displacement and angular displacement. A lot's going on. The analogy is, interesting. You got that's mv vector is I omega vector. Look a lot alike. We talked about this. R vector cross P vector. Yeah, and torque in all its manifestations, in the strictest sense, is looking like that. It's a lot like P vector looking like M V vector, and force is dP vector dt. Look at the analogies. Analogy here. Yeah, we did some stuff here, making it a little easier to look at in some circumstances, but this is more strict. This is more strict. Force equals mass times acceleration. Torque equals I times alpha. You've seen it. Since we're kind of making connections here. Yeah, we got that right there. And then you got this right here. You know, there's two different beasts right here, but that's fine too. That's the torque in that realm, and this is force, and so on and so forth. We said, you know, there is, you know, we said work was FD. I mean, there's more to it, of course. We said work is tau theta. We've been there. Looking at this. We said power is FV, the speed at which the force is being applied. Not momentum. The P's look kind of, you got to be careful. Is this, and that's torque times omega. You know, and it's like I said, L vector is R vector cross P vector, and you saw, wow, how drawn out that could be, but we already proved how a lot of this stuff can play out, you guys, when we're doing this. That should have been this, I'm sorry. All right. And there's more. I mean, there's analogies all over the place. Moral to the story is, let's be aware of it. Those are the chapters for this particular book, chapters 11 and 12, some stuff you might want to look at regarding that. Thank you for your time. We'll talk again.